Hi everyone, my name is Cale from RE Combat Robotics. Welcome to my review of the acquisition of a CR-10 V3 FDM 3D printer. While this may be a little bit different from the normal topics discussed on this channel, it will no doubt be informational to those looking to get into 3D printing themselves. I have several topics to discuss today, such as the selection of the printer, the upgrading process, programming methods, and a final review of the experience. Without further ado, let's get right into the specifics of the CR-10 V3. The CR-10 V3 is the third model of Creality's popular CR-10 series printer. CR-10s are known for their large print volume and widespread aftermarket support. The CR-10 V3 improves upon the previous generations with several included upgrades, such as the diagonal rods which create the golden triangle support structure. Additionally, the V3 has a direct drive extruder included, eliminating the Bowden tube setup that is common on lower-end printers. This improves the speed and accuracy of the V3, something that is necessary when printing large-scale parts. The assembly process was straightforward. However, I took my time to check each component before completing the assembly. 3D printers are finicky, and a slight variation in the setup can change the results by a lot. I checked over the axes belts, drive wheels, and wiring to make sure each component was operational and undamaged. The printer comes with a micro SD card reader and writer in the form of a USB stick. On this SD card were a few test prints programmed by Creality. After only 30 minutes of unboxing the printer, I ran the dog test print with minimal leveling of the bed. Thankfully, everything functioned properly and the dog printed as expected. However, I wanted to test out the printer with a few more models before beginning the upgrading process. The Benchy is a widely used 3D printer torture test, consisting of features that both challenge the printer and show areas to improve upon. For this reason, I chose it as the major model I would be testing my printer with. In order to understand how the printer was printing in a multitude of settings and layer heights, I printed 3 Benchy models, each with a different layer height. I selected 0.16mm for accuracy, 0.2mm for standard printing, and 0.24 for rough prototyping. During the printing process, I was able to capture how the printer forms a large overhang, referred to as a bridge. I had joked that the printer would have to lay filament in mid-air to accomplish this, but I didn't actually expect it to do so. I was pleased to find that each Benchy printed flawlessly. Challenging overhangs such as the front of the hull and the roof showed no signs of failure, and the overall appearance of each model was uniform. However, I did notice a problem that would ruin large-scale prints. The cables leading to the extruder drooped down, touching the bed when the printer was on its lower levels. On a larger print, this could drag across the printed surface and dislodge it from the bed, ruining the print. Cable chains are a common solution for cable management and protection when cables move in one direction. Shown here is a section of cable chains on a Herco CNC milling machine and a printable model I found on Thingiverse. To solve my cable droop issue, I began printing several links and 2 mounting brackets. The first 3 links were functional and would work great for the size of cable I was trying to contain. However, I noticed severe under-extrusion on the print bed and bottom of the print. There should be no gaps between any of the print lines when the printer is functioning properly, whereas I had several. Because of this, the prints were not adhering to the bed and had to be printed with large support structures to hold them down. Under-extrusion is when the printer extrudes less filament than it should, leading to gaps in walls, layers, and an overall much weaker print. This problem can often be fixed by increasing the extrusion percentage. For example, if the printer is printing a line 95% of the proper size, increasing the percent to around 105% should solve the problem. I printed a test box with walls only 1 layer thick to measure the width of the printer's extrusions. The walls should be 0.4mm, equal to the width of the nozzle. However, they were only 0.38mm thick, about 95% of the proper amount. I increased the extrusion percentage to 105% and produced a box with walls 0.41mm thick, much more optimal than the previous 0.38mm. While the printer was now over-extruding, there were no problems occurring from this issue. The difference between the 2 results is obvious when looking at the gaps between layer lines on the newly printed cable chains. With this issue taken care of, I finished printing the cable links and mounting brackets. When printing the mounting brackets, I was able to experiment with supports for the first time. Supports are temporary structures designed to hold up large overhangs and bridges and are made to be removed after the print is completed. Thankfully, the supports I programmed worked well and removed with ease. Once several cable lengths in the mounting brackets were made, I assembled the cable chain and mounted it on the printer. Now, the extruder cables did not sag down and touch the bed, eliminating the risk of print failure from cables touching the print. During my research on the CR-10 V3, I came across a device known as a BL Touch. Creality printers come equipped with software that can store height maps of the printer bed and adjust the z-axes to compensate for hills and valleys, leading to almost perfect first layers with little to no bed leveling. The BL Touch is a probe for the printer head, automatically probing the bed before a print and storing the height map in the RAM. This eliminates the need to manually set the height map or fine-tune for a warped bed. The installation of the BL Touch was straightforward. Most of Creality's printers are designed to have the BL Touch probe installed, so there was already a mounting position on the extruder carriage and wiring plug-in on one of the printer's circuit boards. I was able to route the wiring through my new cable chain as well. While the installation was simple, the BL Touch did not seem to work perfectly out of the box. Specifically, I was running into an issue with the G29 Auto Bed Level G-code. When the printer completes the bed leveling cycle, it is told to move to the corner of the bed and print out a small purge line to prime the extruder and then begin printing. However, as shown here, the printer would move back to the center of the bed and then begin extruding, leaving a line of filament across the center of the bed. There wasn't much support for this error on the internet. However, I found that it was due to how the CR-10 firmware read the G29 code. With a bit of testing, I found that the printer was adding a position move after moving to the corner of the bed, but before the purge line. To solve this issue, I added in a second position move to counteract the phantom move from the G29. Once this was added, the printer worked flawlessly, and I ran a full bed leveling model to see how the printer adjusted itself at each position on the bed. As expected, each corner was printing fantastic, and the printer adjusted its nozzle height during the printing process.
One of the last upgrades I made was increase the nozzle size. Most printers, the CR-10 included, come default with a 0.4mm nozzle, which is great for balancing speed and accuracy. However, when you start to print larger models, such as this Saturn V, it takes a long time. So I drilled out the 0.4mm nozzle and increased it to 0.6mm. This decreased the time that I spent on prints, and it increases the strength. An overall great benefit.
In the future, I am looking forward to printing ABS plastic and other high-temperature materials. However, in order to do this, I had to first place the printer in an enclosure to reduce variations in temperature. This printer bag is a fireproof enclosure that can keep the temperature inside the casing constant when closed, keeping filaments such as ABS and nylon from warping from a quick change in temperature.
RE Combat Robotics has a lot of parts that can be made with a printer such as this. We've already made the handles for our camera rig, GoPro mounts, or even the wiring divider for the Razor's Edge robot. Overall, this was a fantastic project to get to know the finicky nature of 3D printers, but more specifically, the power of additive manufacturing. In the future, I'd love to work with more filament types and optimize printing strategies so we can kick out parts even faster. This video was done through the University of Cincinnati as an honors experience. I hope it gave you a great overview of FDM 3D printing. Be sure to check out other videos on our channel for more updates on the CNC Bridgeport conversion and other engineering projects. Thanks for watching.